Have you ever wondered what keeps us firmly on this ground, preventing us from floating into space? What makes the moon orbit the Earth and the Earth tirelessly revolve around the sun? The answer lies in one of the four fundamental forces of the universe, an invisible yet incredibly powerful glue: gravity. From apples falling in a garden to the majestic motion of distant galaxies, gravity shapes everything. It is the silent architect of the universe, the grand symphony in which we live. But did you know that the story of gravity doesn't just stop at what Newton discovered? There will be many more spectacular discoveries that will completely transform how we perceive the universe. Join us as we explore this profound mystery. Welcome to SpaceTime's journey of cosmic exploration, where we delve into the universe's deepest mysteries. In this video, we will explore the topic, gravity, the glue that binds us to Earth. Don't forget to subscribe to the channel so you don't miss other fascinating cosmic exploration videos. If you find this video interesting and helpful, please like and share to support us.
Gravity is such a familiar part of everyday life that we often take it for granted. Every step, every jump, every time an object falls to the ground, we are constantly experiencing its influence. It is this force that firmly anchors us to the surface of our blue planet, preventing us from drifting into the cold, empty void of outer space. But gravity's role extends far beyond that. It is the grand binder of the entire universe, the silent architect shaping all structures. It is the reason planets maintain stable orbits around massive stars, just as Earth faithfully revolves around the sun. Simultaneously, it also explains why the moon is our only natural satellite, perpetually maintaining an endless dance across the night sky. Gravitational interaction isn't limited to the planetary or solar system scale. It is also the primary driving force in the formation and maintenance of galactic structures, where billions of stars and dark matter are held together. Without gravity, our universe would simply be a chaotic collection of particles without any organization or form. Even the daily ebb and flow of tides in the oceans is a vivid testament to the power of gravity. The gravitational pull of the moon and, to a lesser extent, the sun, creates this rhythmic change, profoundly impacting coastal ecosystems and human life. It is a cosmic dance unfolding right before our eyes.
Gravity is not just an abstract scientific concept. It is a physical reality with far-reaching effects on every aspect of existence. From the smallest dust particles to the largest cosmic structures, all are governed by it. To understand gravity is to grasp a core part of how this universe operates. Before Isaac Newton's time, people held very different notions about motion and forces in the universe, often blending observation with ancient philosophical doctrines. Aristotle once believed that heavier objects would fall faster and that celestial movements followed divine laws, distinct from objects on Earth. This view dominated scientific thought for thousands of years. It wasn't until the time of Galileo Galilei in the late 16th and early 17th centuries that these prejudices began to be strongly challenged through empirical experiments and careful observation. With the use of the telescope, Galileo provided solid evidence supporting Copernicus's heliocentric model, placing the sun at the center. He also demonstrated that in an environment without air resistance, all objects fall with the same acceleration regardless of their mass. Galileo's discoveries laid crucial groundwork for the modern understanding of gravity, breaking down old beliefs, but still failing to connect the fall of an apple with the motion of the moon or planets. It was Isaac Newton, the great English scientist who made the truly revolutionary breakthrough. He realized that the same force that caused an apple to fall from a tree to the ground was also the force keeping the moon in its orbit around Earth.
Legend has it that Newton was inspired when he saw an apple fall in his garden at Woolsthorpe Manor. While this story may have been embellished for illustration, it perfectly encapsulates the grand synthesis in his thinking. From a familiar everyday phenomenon, Newton generalized it into a universal law, applicable to all objects from the microscopic to the macroscopic. He published his Law of Universal Gravitation in 1687 in his classic work Philosophiae Naturalis Principia Mathematica. This law states that every particle in the universe attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This was a powerful statement about the universality of gravity, applying to all matter. The mathematical formula for this law is F equals G times m1 times m2 divided by r squared. Here, F is the gravitational force between two objects. m1 and m2 are the masses of the two objects. R is the distance between their centers, and G is the universal gravitational constant. This constant G, with a value of approximately 6.674 times 10 to the power of -11 Newton meter squared per kilogram squared, indicates the relative strength of gravity in the universe, an extremely small number showing that gravity is a very weak force on small scales compared to other fundamental forces like electromagnetism. Newton's law of gravity successfully explained numerous physical and astronomical phenomena, providing a unified framework for humanity's understanding of the universe. It not only accurately described the elliptical orbits of planets around the Sun, but also allowed scientists to predict the existence of unobserved planets through gravitational perturbations. For instance, small deviations in Uranus's orbit led to the discovery of Neptune in 1846, a powerful testament to the predictive power of Newton's theory.
Furthermore, Newton's law also provided a complete explanation for the daily ebb and flow of tides. The gravitational pull of the moon, and to a lesser extent the sun, draws the masses of water on Earth, creating bulges on two sides of the planet, leading to high and low tides. The difference in gravitational pull at various points on Earth is key to understanding this complex phenomenon. The remarkable predictive power and explanatory capability of Newton's law of gravity were an extraordinary scientific achievement, laying the foundation for classical physics and astronomy for centuries to come. It allowed humans for the first time to have a quantitative and unified view of the forces governing both the terrestrial world and the heavens, ushering in the era of modern science, although some mysteries remained unsolved. Despite the resounding success of Newton's law of gravity, it still harbored several unanswered questions and a few inexplicable anomalies. These points, though seemingly minor at first glance, were the first cracks in the perfect cosmic picture Newton had painted. One of the biggest weaknesses of Newton's theory was how it described the transmission of gravitational force. According to Newton, gravity acts instantaneously between two objects, regardless of the distance between them. If the sun suddenly disappeared, Earth would immediately sense it and fly out of orbit. This concept of action at a distance bothered many scientists. It contradicted other observations of signal transmission, which always occur at a finite speed. Gravitational influence, on the other hand, seemed to happen simultaneously.
Another famous anomaly was the orbit of Mercury. Precise observations showed that Mercury's perihelion shifts slightly after each orbit, a phenomenon called perihelion precession. Most of this shift could be explained by the gravitational influence from other planets, according to Newton's law. However, a small part of the precession remained unexplained by Newtonian mechanics, about 43 arcseconds per century. This was a very tiny difference, but it was a persistent and undeniable problem for the accuracy of astronomical measurements. It signaled that something was missing from Newton's theory of gravity. Furthermore, Newton's law of gravity could not explain how light interacts with a gravitational field. According to Newton, light has no mass, so it should not be affected by gravity. However, some early speculations questioned whether light could be bent when passing near massive objects, opening the door for new theories. These limitations created a significant gap in the physical picture Newton had drawn. They were early signs that a deeper theory of gravity might be waiting to be discovered, especially in cases of extremely strong gravitational fields, or objects moving at speeds close to light. In the early 20th century, as classical physics was at its peak, another great mind, Einstein, emerged and completely changed how we understand gravity. Instead of viewing gravity as a mysterious pull between objects, Einstein proposed a revolutionary new idea. Gravity is not a force, but rather a manifestation of the curvature of spacetime.
This groundbreaking idea stemmed from one of his fundamental principles, the equivalence principle. This principle states that there is no way to distinguish between the effects of a gravitational field and the effects of acceleration. Imagine you're in a sealed elevator without windows. If the elevator is stationary on Earth's surface, you will feel your normal weight. If the elevator is accelerated upwards at a constant rate in space, you will also feel a force similar to weight. Einstein realized that these two situations were fundamentally indistinguishable physically. From this, he boldly deduced that gravity is not a force pulling us down, but rather our reaction to the distortion of space and time around us. This was a complete shift in thinking from force to geometry. To thoroughly explain this idea, Einstein introduced the concept of SpaceTime, a unified four-dimensional network consisting of 3 spatial dimensions and 1 temporal dimension. Instead of being a static stage where physical events unfold independently, space-time is a dynamic entity that can be distorted, bent, and stretched by the presence of mass and energy. Matter does not merely exist within space-time, it also acts to shape space-time. According to Einstein's general theory of relativity, massive objects curved the space-time around them, much like a bowling ball placed on a stretched rubber sheet creates a dent. This dent becomes deeper the larger the object's mass and the closer you are to it. Smaller objects, such as planets or light, when passing through this curved region of space-time, will not follow a straight line, but rather the most natural curved paths known as geodesics.
Let's expand on the stretched sheet analogy to visualize this more clearly. Imagine the sheet as flat spacetime when no matter is present. When a heavy bowling ball, representing the sun, is placed in the center of the sheet, it creates a significant dent or curvature. Now, if you roll a small marble across the sheet at an appropriate distance, the marble will not go straight, but will be guided by the dent created by the bowling ball, and it may begin to orbit the large ball, forming a trajectory. The important thing here is that the marble is not being attracted by the bowling ball by some force in the traditional sense. Instead, it is simply following the path of least resistance, the straightest path in curved spacetime. The orbits of planets around the sun, rather than being the result of a mysterious pulling force, are the result of planets moving along the most natural curves created by the sun's immense mass in spacetime. We are held on Earth
not because a force pulls us down, but because the space-time directly beneath our feet is curved by Earth's mass. The general theory of relativity perfectly resolved the issue of Mercury's perihelion precession, which was a mystery for Newton's law. The curvature of spacetime created by the Sun was precisely calculated, adding a small portion to Mercury's perihelion precession that Newtonian theory could not explain. Einstein's calculations accurately matched astronomical observations, strongly bolstering his new theory. It marked a fundamental shift in how humanity perceives the universe. Einstein's theory was not just a beautiful idea or a complex mathematical work, it also made bold predictions that could be experimentally verified. And these verifications have consistently confirmed the correctness of the general theory of relativity, ushering in a new era for physics and astronomy, solidifying its position as one of the most successful theories of all time.
The first and most famous prediction was the bending of light by a gravitational field. According to Einstein's theory, light, despite having no mass, would still follow the curves of spacetime when passing near a massive object. This meant that light from a distant star, when passing by the Sun, would be slightly bent, causing the star's apparent position in the sky to shift. In 1919, astronomer Arthur Eddington organized an expedition to Príncipe and Sobral, Brazil, to observe a total solar eclipse. During the eclipse, the Sun's dazzling light was obscured, allowing Eddington and his team to photograph stars near the Sun's limb. When comparing the positions of these stars to their positions at night, they found that light was indeed bent exactly as Einstein predicted. This was a resounding triumph, making Einstein a global scientific icon. Another important prediction was the phenomenon of gravitational redshift and time dilation. This theory states that time will pass more slowly in a strong gravitational field. This means that a clock placed near a massive object will run slower than a clock in a weaker gravitational field. This effect has been verified numerous times, most notably with GPS satellites. Atomic clocks on GPS satellites orbit at high altitudes, where Earth's gravitational field is weaker. According to the general theory of relativity, these clocks would run faster by about 38 microseconds per day compared to clocks on the ground. Without adjustment, the GPS system would accumulate errors of several kilometers per day. The daily accurate operation of GPS is a vivid, practical proof of the general theory of relativity.
Most recently, and perhaps one of the most spectacular pieces of evidence, was the direct detection of gravitational waves. The general theory of relativity predicted that the most dramatic cosmic events, such as the collision of black holes or neutron stars, would create ripples in spacetime, propagating throughout the universe at the speed of light. These ripples are called gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by directly detecting gravitational waves for the first time from the merger of two black holes billions of light-years away from us. This discovery not only opened up an entirely new field of astronomy, but also powerfully confirmed Einstein's final prediction about gravity. Since then, LIGO and other observatories have recorded dozens of gravitational wave events, providing profound insights into extreme objects in the universe and allowing us to listen to the cosmos instead of just seeing it. Gravity is not merely a force that holds us to Earth or bends light. It is the grand architect that created and shaped the entire structure of the universe we see today. From the birth of stars to the formation of colossal galaxies and the cosmic web, everything is governed by it. Without gravity, the universe would simply be a chaotic, shapeless sea of matter.
When enough mass concentrated
the pressure and temperature within the core rose extremely high, sufficient to trigger nuclear fusion reactions. And so, a star was born, blazing brightly in the dark expanse. Gravity continued to maintain the star's stability, perfectly balancing the outward pressure from nuclear reactions. Around newly formed stars, remaining dust and gas particles continued to swirl in a massive accretion disk. The central star's gravity, along with interactions between the particles, gradually caused them to collide, coalesce, and grow larger, forming planets, asteroids, and other smaller objects. This is how planetary systems are formed. On an even larger scale, gravity gathered billions of stars, vast amounts of gas, dust, and a significant quantity of dark matter together to form galaxies. Our galaxy, the Milky Way, is a prime example, where hundreds of billions of stars are held within a colossal spiral structure by gravity. These galaxies are not static. They gravitationally interact with each other, sometimes colliding and merging to create even larger galaxies. Galaxies, in turn, do not exist in isolation. They gather into galaxy groups, and then into colossal galaxy clusters. On the largest scales, the universe has a giant network-like structure known as the cosmic web, with galaxies concentrated along filaments and vast voids between them. All these structures are products of gravity on a cosmic scale. Speaking of gravity, one cannot help but mention black holes, the most mysterious, extreme, and fascinating entities in the universe. Black holes are regions in space-time where the gravitational field is so incredibly strong that nothing, not even light, can escape once it has passed an imaginary boundary called the event horizon. This is a place where all paths lead inward, with no exit. They typically form from the gravitational collapse of massive stars at the end of their lives. The star's core runs out of fuel, no longer having enough pressure to resist gravity, and it rapidly collapses into an infinitely dense, minuscule point called a singularity. Additionally, there are supermassive black holes located at the centers of most galaxies, with masses equivalent to millions or even billions of suns. At the event horizon of a black hole, space-time is curved to such an extent that all paths lead inward. If you cross the event horizon, you cannot return. Inside a black hole, the laws of physics as we know them seem to break down at the singularity. An object falling into a black hole will experience spaghettification, being stretched into a long noodle due to the enormous difference in gravitational force between the object's head and feet. Scientists have indirectly observed black holes through their gravitational influence on surrounding stars and gas, or by detecting X-rays emitted from matter being drawn into the black hole. Recently, the Event Horizon Telescope captured the first direct image of the shadow of a supermassive black hole, a historical scientific achievement. Gravity also plays a crucial role in the existence of two of the universe's most mysterious components, dark matter and dark energy. Dark matter is a mysterious form of matter that does not interact with light, but has significant gravitational effects. We know it exists due to its gravitational influence on the rotation of galaxies and the distribution of matter in galaxy clusters. Dark energy is even more enigmatic, a form of energy believed to be accelerating the expansion of the universe, countering the gravitational force that tries to pull everything together. These two components, dark matter and dark energy, account for approximately 95% of the universe's total energy and matter. This indicates that,
Although we have come a long way in understanding gravity, much remains unknown. Although Einstein's general theory of relativity revolutionized our understanding of gravity on large scales, it remains incompatible with another successful physical theory of the 20th century, quantum mechanics. Quantum mechanics accurately describes the world at extremely small scales, the atomic and subatomic levels. The fundamental conflict lies in the nature of each theory. General relativity describes spacetime as a continuous, smooth entity. Quantum mechanics, on the other hand, depicts the world using discrete quanta and interactions mediated by particles. Problems arise when physicists attempt to apply both theories to extreme situations, such as inside black holes or immediately after the Big Bang.
At these points, mass and matter density become incredibly immense, and space and time are also distorted to such an extent that quantum effects become extremely significant. The equations of general relativity and quantum mechanics cannot operate together. They yield contradictory or even meaningless predictions, indicating that one or both theories are incomplete. The grand goal of modern physics is to seek a theory of quantum gravity, capable of unifying general relativity and quantum mechanics into a single, coherent framework. This theory would allow us to accurately describe the universe at all scales, from the smallest particles to the greatest structures of galaxies, and to understand the universe's earliest moments. One of the leading candidates for a theory of quantum gravity is string theory, which proposes that fundamental particles are not points, but rather tiny vibrating strings of energy. Another candidate is loop quantum gravity, which attempts to quantize spacetime, suggesting that spacetime consists of tiny, discrete quantum loops. A theory of quantum gravity would also have to explain the existence of the graviton, the boson particle that mediates gravitational interaction. While other fundamental forces have their corresponding force-carrying particles, the graviton remains only a hypothesis. Unifying the fundamental forces of the universe is one of the greatest challenges of modern physics. Our journey of exploring gravity has taken us from Newton's falling apple to Einstein's space-time bending black holes, and now to the mysteries of dark matter, dark energy, and the aspiration for unification with quantum mechanics. Each step forward opens up a deeper insight into the complexity and beauty of the universe. But how could Albert Einstein have conceived such a revolutionary theory as general relativity? A theory that forever changed how we understand space, time, and gravity. In our next video, we will delve into Einstein's general relativity, how the universe works, exploring the groundbreaking ideas that shaped modern physics and continue to challenge our understanding of reality. Don't miss it.